we'll go on to the next problem, which is number 3. Okay, the selection problem. Okay, selection problem usually gets people a bit nervous, so I'm going to give you a bit more support here, right? So you have a telescope built using a single lens, provided that a small aperture is used instead of an eyepiece. So this context obviously assumes that you know what a telescope is, right? A telescope, right? Let's say the Keplerian refracting telescope, right? Is basically made up of 2 lenses. Okay, one is the objective lens. This is the one that is in front. Okay, and then you have an eyepiece behind. Okay, so this lens system gives you, right, is the basic things that you need for a telescope. So now what you are required to do is that replace this eyepiece with a small aperture, okay, namely a pinhole, a hole, that's all. Okay, right, so a lens and a hole cannot be too difficult, right? Okay, right, it's not, it's not lethal, a hand lens and a hole. How do the parameters of the lens and the hole influence the image? Okay, right. So in this case here, you can see we are putting basically 2 things together. Right. You should understand basic principle behind a refracting telescope, and then next is how does a pinhole camera work? Okay, right. 2 things, 2 questions. Okay, right. So I'm not going to go through this, right? But this is basically how a 2-lens system, okay, right, gives you magnification, okay, right? So I'm not going to give you a lecture for this. I have a paper for you, okay, right? So I don't think I'm going to remember seeing this paper. So anyway, 1 paper for this. That's all. Then I'll give you a paper on the digital pinhole camera. Okay, right. So this paper basically outlines how you can build your pinhole camera, okay, and how you can put a digital camera behind, and how this whole thing can allow you to study the properties of the pinhole camera. Okay, I will give you a few papers that talks about theory. Okay, right. 1 and a few. Okay. Now the physics of the pinhole, right? Even though because it's a hole, right? Okay. So the hole size is the one that actually determines the optics. Okay, right? So hole size, you should know that if you go to very small hole size, then physical optics will come in. Okay, right? So for the selection problem, you notice that I selected with hopefully care. Okay, I think a lot about it. Okay, these are problems that where if for the high schools, right, if you just stay on the geometrical optics side, okay, you are excused. Okay, right? For the Sec 4s and for the Cat A students, right? Okay, I'm afraid you have to push yourself a little bit more, okay, and go into the physical optics, right, regime. Okay, then if you think that this problem is easy, okay, digest this paper. Okay, this one, right, this is where they actually take into account both hole size, that means sort of like, a theory that can accommodate both geometrical optics as well as physical optics together. Okay, and then they talk about the transfer function. Okay, right, so these are the last 2 papers, okay, for pinhole. And don't forget our lens. You have to put the lens and pinhole together. Okay? Right, so how to put lens systems or optical systems together requires a little bit more of optics. Okay? So I will give you 1 chapter from a book. Okay? Geometrical optics. So inside there you will find how you can actually combine different lens systems using linear algebra, okay, methods. Okay, right, and hopefully that will be sufficient material for you to prepare for the selection. Okay, yeah. Questions? Right. So far, first two questions, Cat B, and then selection question number 3. Problem number 4 is the first Cat A problem. Right. You have a small amount of ferrofluid. Okay. What is the ferrofluid? Okay. First thing. Right. If any of your opponent would say, I take iron, I foul, I put it inside oil, straight away die. Okay. That is not a ferrofluid. Okay, right, iron foulings are micron size. Ferrofluids, right, the magnetic particles are nanometers. Okay, 10 to the minus 9. Okay, right, so you cannot just take iron foulings, put inside oil, and then say, okay, I have a ferrofluid. Okay, right, so this ferrofluid, if you want to make it, will be a little bit challenging. Okay, so the iron foulings that you have to foul continuously for another 2 weeks until it becomes nano size. Okay, after that you have to chemically deposit a layer, okay, right onto the nanoparticles. Okay, so that is you need chemistry techniques. Okay, right, and then lastly you have to find a suitable liquid to suspend all these particles. Okay, right. So therefore, advice: go and buy. Okay, but when you buy, make sure, right, the supplier can give you detailed properties, details, okay, of the properties of the ferrofluids. Okay, what details? I don't think I need to show you which table to go to. Among the papers that I give you, okay, you have a paper that listed down the detailed, information about the different properties of ferrofluids that you can play around with. Okay, right. So this is one. Next, in inhomogeneous magnetic field. Okay. So just now Marcus said that if you read the papers, okay, it's fine, but sometimes it's wrong. Okay, it's not because it's wrong. Okay, right. Most of like this problem here, okay, all the papers that you can find in the market, at least until now, I tried very hard. Okay, they are about homogeneous magnetic field. Okay, right. So this phenomenon has the name. It's called normal field instability. Okay, but the physics wouldn't change. Okay, in other words, whether I believe, this is my belief, I may be wrong again. Okay, right, is that whether you have uniform or non-uniform magnetic field, the physics won't change. It's still normal field instability. Okay, right, but of course there will be features that will be different. Okay, right, why? Because in a normal field, usually the setup is that you have, in this case, of course, we do not have uniform magnetic field. These are all non-uniform. These pictures are all taken by Mr. Lim. Okay, right, so they are from our nanofluid which arrived 2 days ago. Okay, right, right. So in this case here, okay, normally, okay, in the papers when they discuss, those normal field instability are all concerned with uniform field, homogeneous magnetic field. Okay, right. So therefore, you cannot take wholesale from the papers, right? Because usually our Singapore mentality is that you go flip the 10-year series to the back, right? Then you get the answers. Okay. The purpose of the papers is not for this. It's not your 10-year series where you flip to the back and you find answers. Okay. Right. So bear this in mind. It's very important. Okay. Yeah. So inhomogeneous fields. Inhomogeneous fields. What will it give rise to? If you look at the uniform field, right? The spikes. Okay. They will be uniformly distributed over the surface. Okay, in the presence of a non-uniform field, the number density can be different. In other words, there may be more spikes at some area, less spikes at some other area. Okay. Second, the size. Okay, the size, okay, of these spikes. There will be some bigger in size, some smaller. Okay, right. And then the shape. Okay, same thing. Right, shape, size. Okay, right. So you have slightly different geometries for inhomogeneous magnetic field. Okay, right. So I give you the keywords. I'll give you some papers that will start you off understanding what ferrofluids are. I will give you an original paper on ferrohydrodynamics, and then Yeah, some of this experiment paper on this well-known normal field instability. Okay, right. I have some nano fluids here. I think I'll pass it around. Can I pass it around? You promise me you will not destroy it, right? Okay, right. Try to, okay, still, so it should be okay, right? Try to move it around, okay, right? Because usually the pictures that we see here, they are all static, right? But in fact, this thing is not really static, as in it is, you can see it forming, right?